Welcome back, students. In this video segment, we will cover one section, section 6.4 star or asterisk, general logarithmic and exponential functions. So let's go ahead and get started. Okay, this is a relatively minor section in the scheme of things in terms of math for STEM majors. In fact, I'm of the opinion that this section could actually be omitted from the course without missing anything at all important for STEM majors. The course is in the standard course outline though, so we're going to cover it. It's a minor section, and I'll explain along the way why I think it's kind of a minor section. In this section, we'll cover exactly what the title says. General logarithmic and exponential functions means logarithmic and exponential functions that are not natural logarithm or the natural exponential function. If you've had chemistry, you've most likely seen the common logarithm very early on when you studied pH, or the power of the hydronium ion concentration. I'm not a chemist, so if my language isn't good on that, you'll please forgive me. But if you'll recall, if you've had chemistry, that the pH is equal to the negative of the logarithm of the hydronium ion concentration. Okay. And what that means is that we're using the common logarithm. A common logarithm is logarithm base 10, and you notice in the expression the base is missing. We could put it in, there's nothing wrong with it, but it's generally not written with the common logarithm. The base is not written. It's just understood to be a base 10. Okay. Other than the common logarithm, I haven't seen in STEM-based math logarithms or exponential functions with bases other than either 10 or the base of the natural logarithm e. So it's for that reason I think this is a relatively minor section. Nonetheless, let's go through the section. The idea is to be able to integrate and differentiate functions involving logarithms of bases other than 10 or e, and exponential functions with other bases. Okay, so let's get started. First thing let's take a look at is the concept of the derivative of the general logarithm function. So let's say let f of x equal a to the x. Okay, where a is the base of this exponential function, and the usual restriction on the base is that the base is some number between 0 and 1, or something more than 1. We don't have 0 as a base, or negative numbers as a base, or 1 as a base. Specifically, if we let the base be 1, we're looking at y equals 1 to the x, which is just 1, y equals 1, which is a horizontal line, and it doesn't exhibit the properties of an exponential function that we're used to. Namely, it's either exponential growth or exponential decay. It's just a horizontal line. So that's an example of why we don't allow all the bases for the exponential function. So let's concentrate first on a formula for finding the rate of change of the function, the derivative of a to the x with respect to x. I'm going to use a little trick to do that. The trick is that the exponential function and the logarithm functions are inverses of one another. So what I'm going to do is I'm going to write a to the x as e raised to the ln of a to the x. Okay, if I do that, the e and the ln would cancel. We get back to a to the x. So this is in fact an identity. Then I'm going to use the third of the big three principles for logarithms, and in that exponent, I'm going to bring the x down as a coefficient of ln a. So I'm going to write this as e to the x times the natural log of a. Okay, so this is just e to the constant multiple of x, e to the some constant multiple of x, and we can find the derivative of e to the constant multiple of x. For example, suppose I wanted the derivative with respect to x of e to the 3x, something simple from our past section. This would be e to the 3x again, times the derivative of the exponent by the chain rule times 3, or 3e to the 3x. So I'm going to apply that idea to our situation. I want the derivative with respect to x of a to the x. Well, that's going to be the derivative with respect to x of e to the x times ln a, x ln a, where ln a is sort of like the 3 in e to the 3x in the green example above. So let's take the derivative using the chain rule here, just like we did with e to the 3x. Well, the derivative of e to the x ln a is e to the x ln a again. Then by the chain rule, since ln a is constant, the derivative of ln a times x, or x ln a, is just natural log of a. So it's just e to the x ln a times ln a. Okay, but remember, e to the x ln a is just a fancy way of saying a to the x by the identity that I'm highlighting in red again above. So this is just a to the x times the natural log of a, and that's the first of a very few big formulas in this section. This says that the derivative with respect to x of a to the x is a to the x times the natural log of a. So this is our bottom line with the derivative of exponential functions of sort of arbitrary base. Let's take a look at an example. So, for example, let's find the derivative. So let's differentiate, what that means, find the derivative. Part A, let's say y equals something real simple, 7 raised to the x. Okay, so y prime, look at the formula above, the derivative of a to the x is then a to the x again, times the natural log of the base, natural log of a. So the derivative of 7 to the x is 7 to the x times the natural log of 7, and that's it. There's nothing else to do with that. Part B. Let's up the game a little bit. So let's say y equals 7 to the x squared. So the derivative then is the derivative of 7 to a power is 7 to that same power again by the formula in red above, times by the chain rule the derivative of the exponent. Derivative of the exponent would be 2x. So we could either leave it that way or write it as 2x times 7 to the x squared. And that's it. There's nothing else to do with that, really. Part C. This is where things get a little different. This is probably if there's one thing in this section I think really does belong here, this is the example. Suppose we look at something like y equals x raised to the x power. Now think about that here. The base is not constant, like in the red formula above, a and a to the x is constant, and the exponent's not constant. So we have really a very different function than we're used to here. We have a function raised to another function. So there's a common misconception with how to take the derivative of this function. I'm going to show you the common things that are done wrong. So let's see. Let me identify it this way. It would be wrong to do this. So let's see. Remember how if you have something like x squared, let's make it a little bigger, exponent x cubed, then y prime equals 3x squared. That's correct. That's right. So the incorrect thing would be to assume that you can do the same thing if you have, like, instead of x cubed, you have x raised to the x. Oops. And then of course I wrote cubed again. X raised to the x power. It would be absolutely incorrect. It would be absolutely incorrect to say bring the power down, decrease the power by 1. This is an absolute no. There's nothing in Calc 1 that says that we can do this. This is no. We can't. I don't even want to put equals here. This is just not true. This is, well, I'll put it there. It's not true. No. We can't do that. It's also common to misuse the formula that we just looked at today. So for example, if you have y equals 3 to the x, the one I started with, it is correct that y prime equals 3 to the x. It's an exponential function times the natural log of 3. This is correct. Absolutely correct. But it's incorrect to try to use that idea with x raised to the x. If I did that, I would be writing x to the x times the natural log of the base, and that's another no-no. It's a real big no-no. You can't do that. So this is different than both of our previous interpretations of how to take the derivative of functions where either the base is constant and the exponent is variable, or vice versa. The base is variable, exponent is constant. I wonder if I said the same thing. Okay, so we have to be a little careful with this one. So how do we take the derivative of a function raised to another function? Well, the answer is easy to state. We use logarithmic differentiation. Logarithmic differentiation. So let me redo this with blue. The correct way, the correct thing to do. Current. I don't know where that came from. The correct thing to do is to use something that we studied previously, logarithmic differentiation. We'll use logarithmic differentiation, and I'll show you how to do that after I spell differentiation. Okay, so let's do it. So here, if y equals x to the x, take the natural logarithm of both sides, and we get the natural log of y equals the natural log of x to the x. And here's the next step, is why we're using logarithmic differentiation. That exponent in x to the x can now be brought down as a coefficient using the third of the three big properties of logarithms. And now we can take the derivative of both sides without having to worry about the exponent being a variable anymore. So let's do that. So since we're not looking at y explicitly, we're going to use implicit differentiation here. So I'm going to take the derivative of both sides using implicit differentiation. So we get 1 over y times the derivative of y prime. And on the right-hand side, we have the product of two functions. So I'm going to use the product rule. The derivative of the first function is 1 times the second plus the first function times the derivative of the second, 1 over x. So we're basically there. Let's simplify this right-hand side a little bit. We'll get rid of the 1 as a coefficient, and x times 1 over x is 1. So that's 1 over y times y prime. Then I want y prime by itself. Remember, we're after the derivative, the rate of change. So I'm going to multiply both sides by y, and we get y times, on the right-hand side, the natural log of x plus 1. So we have an explicit solution. Then the derivative, then substituting the original y as x to the x power, is x to the x times natural log of x plus 1. Totally different kind of function that we're used to. Totally different. A function raised to another function. So when you're dealing with function raised to another function, this is what you do. This is one good possibility. I don't know of any other way to do this actually. Logarithmic differentiation. Logarithmic differentiation. Okay. Okay. So now let's look at integrals involving bases other than e. Bases other than e. So in order to do that, we're going to take a look at the derivative form that we have for today, the only new form really. The derivative of a to the x is a to the x times the natural log of a. Now I want the integral, the most general antiderivative of a to the x. So I'm going to, basically I'm going to take the antiderivative of both sides of this expression. So if the derivative of a to the x times if the derivative of a to the x is a to the x ln a, then the antiderivative of a to the x times the natural log of a should be a to the x plus a constant. I'm going to label the constant C1 for a reason that will become apparent in about 15 seconds or so. Okay, so what I'd like though, I don't want the integral of a to the x times the natural log of a. I want the integral of a to the x. Natural log of a is a constant. So remember, constants can be factored out of the integration process. So I get natural log of a times the integral of a to the x equals a to the x plus a constant. I'm going to divide both sides by the natural log of a, and we get our result. Okay, so we get a to the x over the natural log of a plus C1 over the natural log of a. Now the reason I wrote C1 instead of just C for the constant of integration is I want to clean up that final constant. The natural log of a is just a constant, and C1 was arbitrary. That means it was just any constant. So I'm going to replace C1 over natural log of a with another arbitrary constant. And that's our integral formula for the general exponential function. So let's take a look at an example. So example. Earlier I mentioned that the common logarithm, base 10, is used early on in chemistry, general chemistry, for pH. So let's suppose we want the most general antiderivative of the function, the inverse of that common logarithm. Let's say 10 to the x. Remember, 10 to the x is the inverse of log base 10 of x. This is very simple. The only thing we need to do is apply the formula that we just looked at with the base of 10. So it's 10 to the x over the natural log of 10 plus a constant. What if I wanted to use this formula for something we already know? We know what the integral of e to the x is. It's e to the x plus a constant. So we should be able to use this formula for any base, though. The only restriction on the base is that it's either a number between 0 and 1 or more than 1, and e is definitely more than 1. It's about 2.72. So the most general antiderivative of e to the x then is e to the x over the natural log of e. Well, what's the natural log of e? The natural log of e is 1. E is the base of the natural logarithm, and it's always true that the logarithm of the base of the logarithm is always 1. Okay, so if you missed that, this is since ln e is log base e of e, and that's just 1. Okay. Slightly more complicated problem next, or example next. Suppose I want the most general antiderivative of, let's say, 10 raised to the square root of x over the square root of x. We're going to be doing a lot of integration very, very soon. So this is sort of looking into it. This is an early glimpse into our future with this problem, but not too complicated. For this problem, a simple u substitution will work real well. Let's see, did you think of it? You want to try to think about it? What u substitution should I make? What u substitution? Well, it's pretty clear that what separates this problem from the first part of this problem, the 10 to the x problem, the integral, is that we're looking at the square root function in the exponent. So first try might be to let u equal the square root of x. Okay. So if u equals the square root of x, then du equals, remember square root of x is x to the 1/2. So the derivative is 1/2 x to the minus 1/2. And then to get the differential, we multiply by dx. So this is 1 over 2 radical x dx. Remember, x is the negative 1/2. The negative brings the expression down into the denominator, and 1/2 means square root. So 1 over the square root of x dx equals 2 du. Okay, so let's make the substitution into our integral and go forward. We're looking at 10 raised to the u, 10 raised to the u, and dx over the square root of x, or 1 over square root of x dx, is just 2 du. The 2 is a constant. Constants can be factored out of integral signs. Nothing else can be factored out. And then we're done. Basically, the integral of 10 to the u is 10 to the u over the natural log of 10 from our integral formula that's squared off in red up there. U was the square root of x. So this is 2 times 10 to the square root of x divided by the natural log of 10 plus a constant. Okay. All right, so let's take a look at the general logarithm function. We looked at the general exponential function a to the x. Let's see if we can get a derivative of the function log base a of x. So suppose I let y equal the logarithm base a to base a of x, and I want the derivative. Well, we could one thing we could do is transform this function to a natural log function by using something called the change of base formula, but we don't even need that. What I'm going to do is I'm going to get at the derivative of this function by using the definition of logarithm that we talked about in a previous section. I want you to remember, take a look with me at a real simple example. So recall, if you have something like the logarithm base 3 of 9 equals 2, this means that 3 raised to the second power equals 9. Okay, that's how we actually define the logarithm. Logarithm always equals an exponent, the exponent that we raise the base to get the quantity we're taking the log of. I know that sounded pretty funny, but it's true. Okay, so let me put our expression right beneath that. Log base a of x equals y, just sort of writing it backwards from how I started it. Backwards, instead of writing y equals log, I write log equals y, and then use the process I just described for the green natural log of 9 with respect to 3, log of 9 base 3. Talk a little too fast. So this is a to the y. A raised to the y equals what? A raised to the y equals x. Okay, so I'm going to use that form to find the derivative. going to use the form. It's still our same function. It doesn't look the same, but it's the same function, just written solved for x instead of solved for y. You solved written in exponential form. So let's take the derivative. Let's take the derivative with respect to x. I'll just insert the derivative operator on both sides. Derivative with respect to x, both sides. And remember our formula for the derivative, a whole bunch of lines above, that the derivative with respect to x of a to the x is a to the x times the natural log of a. We talked about that about 10-15 minutes ago. Let's use that here on the left-hand side. Derivative of a to the y is a to the y natural log of a times what else, though? What else? Well, we're not taking the derivative of a to the x, we're taking the derivative of a to the y. So what does implicit differentiation say we multiply by? Y prime. And the derivative of x with respect to x is 1. We're almost there with this. If we divide both sides by a to the y times natural log of a, we get y prime equals 1 over a to the y times the natural log of a. It's almost there. But what was a to the y? Look above a few lines. Look at the red arrow. A to the y is x, so that little a to the y in the denominator can be written as x times the natural log of a. So that gives us our last formula. It gives us our bottom line, that the derivative with respect to x of the logarithm base a of x is 1 over x times the natural log of a. So what if I wanted the derivative with respect to x of the common logarithm, log base 10 of x? Super simple. By the formula, by our big formula for right now, our last big formula, this big formula says that the derivative of the log base a of x is 1 over x times the log of a. So it's 1 over x, in our case, times the natural log of 10. So this should work for ln x. It should work for any base, the log of any base. Now let's see how it works. We know the derivative of natural log of x. It's 1 over x. Well, let's see if this formula works. Natural log has a base of e, and our formula then says the derivative is 1 over x times the ln of the base, ln a. A is e in this case. And remember, e again is such that the natural log of e is 1. We get what we expect. Okay, well, what if we want the derivative of the log base 3? I can't imagine where you would have that happen in STEM math. But suppose we wanted the derivative with respect to x of log base 3 of sine of x. Okay. Looks like a terribly complicated function. It's not. Use the chain rule and our formula. We have a composition of two functions, log base 3 and sine. So by our formula, derivative log base a is 1 over x. Well, we don't have x, we have sine x. So the chain rule says to take the derivative of the outside function, log base 3, but you evaluate it at the inside function. And then you multiply that by the formula that I'm putting a little red arrow on above, by the natural log of the base. Is that it? Think about it. Is that it? And you're thinking maybe, well, if he's saying, is that it? That's probably not it. And you're right. We have to take the derivative of the inside function by the chain rule. This is something that a lot of students forget or neglect to do, is to take the derivative of the inside function. We can maybe clean this up a little bit. Can you see a simpler expression for this? Can you see a simple expression for this? Well, we could write the cosine on top, but yeah, what's cosine over sine? It's cotangent, so we could write this as cotangent of x over the natural log of 3. We could also leave it as just cosine of x over sine of x times the natural log of 3. But the answers in textbooks tend to be a little fancy as possible, although they're not consistent. Either's okay, though. Either's okay. Alrighty. So there were, just to recap, there aren't that many formulas in this section. This is a really, really short section. The main formulas for this section are the derivative with respect to x of a to the x, which is 1 over x times the natural log of a. The antiderivative, most general antiderivative of a to the x, which is a to the x. Wait a second. Make sure I wrote it right above. Sorry, folks. I apologize, folks. Had a little bit of glitch, not with the computer so much, but with my my formulas. So rather than edit this out of the video, I think I'll keep it real and just fix my formula. The derivative of a to the x is not 1 over x ln a. So it's a to the x ln a. The most general antiderivative of a to the x is a to the x over ln a. That's a constant. And finally, the derivative with respect to x of log base a. Oops, log base, not alpha, but log base a of x is 1 over x ln a. And again, I apologize for my brain glitch above. All right, and this ends this section. It's a very short section this time, and the section was section 6.4 star, the general logarithmic and exponential function, and I'm looking forward to talking with you all again soon.